All right. So we're going to go into the next section. So we're starting in chapter 5, and chapter 5 is all about um, a different proof technique. It's going to be what's called mathematical induction. So what we're going to do, so we learned the sort of direct proof methods and indirect proof methods. And now what we're going to do is sort of learn a slightly different technique. And so that's induction. I'll say induction is one of the places where it's maybe the least intuitive thing to prove something this way. But to be honest, I think induction is actually a lot easier than many people often think that it is. And I hope this will show you that it's not so bad. So I'm going to run through the proof of this theorem. So it's the theorem is for all finite sets A, if here, right, you remember this little thing that we have here. Let me get a pen, draw this, right? What that means is basically the cardinality or size of the set, right? So if A has n elements, right, remember then this over here is saying that the power set has 2 to the n elements. Now the book has a few examples of it. You can write them out for yourself if you'd like. But, it's not particularly difficult. Now, what they're saying is for all finite sets, right? So when it says for all finite sets, what does that mean? Well, the finite sets, they can have 1, well, they can really have 0, right? Empty set is a thing. 1, 2, 3, ... right? So we could have this many elements in the set, right? So n could be any of these numbers. So what does mathematical induction tell us we can do? Well, we can show, right? How am I going to prove by induction? So how? Right? Well, we show, and I'm going to use some slightly different notation. I'm going to say show that P of, in this case, 0 is true, right? This is the basis step, right? And when I have this, I think the book does it this way, so we'll do a P with a little 0. Basically, right, I'm going to prove that it's true that the statement, right? And what is the statement? Well, we can think of the statement as being this thing up here. For all finite sets A, if the cardinality of A is n, then the cardinality of the power set for A is 2 to the n, right? This, right, this whole statement, right, we could call this, I'm going to say it's P of n like this, right? I want to show that it's true in the basis step, right? I want to show that P of 0 is true. And that's what they do here, but I'll walk through it, right? So how do I show, right? So basis. Let A be a finite set. Well, I'll just say let A be a set with no elements. Right, an equivalent way of writing that would be to say let A be a set where this is true, right? Well, what do we know? There's only one set with 0 elements, right? So we know that A is equal to the empty set, right? The only set with no elements is the empty set, right? And, right, what do I know about the power set of A? Well, I know that that's just the set that contains the empty set, right? So, is this true? Well, I know that this is 1, right? Because I can just count, right? And 2 to the power of 0 is also equal to 1. So in fact it is true, right? The basis step, I can prove it true this way. So I just let it be a set with no elements, right? That means that the size or cardinality of A is 0. That means A is the empty set, and we know that since A is the empty set, right, the power set of A, right, the power set of A is just the set that contains the empty set, right? I know that this is true because I can just count, right? How many things are in here? Well, there's only one set there's only one element inside my power set. The only element is the empty set itself there. So I know that that's true, and I know that 2 to the power of 0, because remember, n is equal to 0 in this case, I know that 2 to the 0 is actually 1. Right? If you want, you could say, therefore, right, it's true. That's not necessary. It should be obvious that it's true. So the next thing we want to do is we want to do the inductive step, right? So the first thing is the basis step. The next thing is the inductive step. The way I always think of the basis step is sort of like I'm like building a foundation with the basis step, right? Sort of, if I go down far enough, right, this is, the sort of smallest element in the set of all of the things I'm doing, right? In this case, it's 0, right? 0 was the smallest number we could have, right? It was the smallest natural number. And so, in this case, it makes sense to have a set with 0 elements. Right? Now, as you'll find out, sometimes we may not want to have the domain be all of the natural numbers. Maybe it's like all numbers greater than 1 or greater than 2. So don't get too hung up on that, right? It works out just fine as long as we have a smallest number that exists in our set. We're perfectly fine with that. So I sort of build this foundation, and the next thing is kind of weird, because what we're going to do is we're going to show right? We're going to now prove this, right? We're going to prove this. And the way we do it is we make use of the inductive hypothesis. An inductive hypothesis is really just supposing that this is true. Now notice this is the way that we actually proved universal conditional statements, right? When we were doing conditional statements and direct proofs. We sort of supposed that the hypothesis is true, right? And then we deduced a true conclusion from that. And that's essentially what we're going to do, right? We're going to suppose that P of K is true. Now, what does that mean for our purposes? It means that this statement up here is true for some member of the natural numbers K. From that, what we're going to do is we're going to deduce that it must be true for the K plus 1 member, right? So really, what we've done is we've built a sort of foundation with the basis step, and we're going to start building up on top of that, right? By supposing it's true for some element K of the natural numbers, right? And you'll see how this works. So let's start by suppose, and this is a little different than the way the book is doing it. Suppose I'm going to say P of K is true, right? So what does that mean? So that is, right, that then and here I guess it looks kind of weird because I'm using the power set notation, and I'm also using P to also mean my sort of like sentence statement up there, but hopefully you can right. So we're going to suppose that this thing is true, right? The hypothesis is true. And we want to show that for some other, let's say, some other set, right, that has K plus 1 elements, right? So let's just take a second, right? And think about this. What I'm going to do is I'm going to let, here I'm going to use a slightly different notation. I'm going to let A prime be a set such that the cardinality of A prime is K plus 1. Now, what do I want to do? I want to show that the power set of A prime actually has 2 to the K plus 1 elements in it. So let's talk about how I'm going to do that. And what I'm going to do is I'm going to like make a little line here, and I'm going to give an example of what's going on, because sometimes it might not be obvious from what's going on in the book, or I mean, I could just say, suppose that S1 is a subset of the power set of A prime, and S2 is a subset, and we choose some element of A prime, we'll call it A. We could make the two subsets where, A is a member of the subsets of S1, and then then it's not a member. It's not in sets in S2 or something like that, but I'm going to do a very small example, right? Let's just consider this set. So here's a set, right? 1, 2. Okay. And so let's do the power set of this. What's the power set of this? Well, remember that the empty set is there. All the singleton sets. And then the set itself here. Okay. So notice I can choose an element in here, right, in the power set, or in the original set, right? So let's say, right, I choose the element 1, right? So notice I can construct some subset of this power set where it's the set of all the power sets that contain the number 1. And notice I can create another subset, S2. Right. That is everything that doesn't contain the element 1. So there's the empty set, and there's the singleton set that just contains 2. Now, something kind of nice that happens here is that this has 2 elements, right? And this has 2 elements, right? Also, another thing to look at is that these subsets are actually disjoint subsets, right? Meaning that the intersection is the empty set, right? That the intersection of these two sets, actually, they don't contain any of the same elements. So that's actually kind of nice. And the union of the sets is the power set itself, right? something that's kind of nice here, right, is that if I look at the size of this, right, I guess I shouldn't have written an equal sign here. It's 2, right? And notice, right, when I think about these things, right, this set is kind of made well, I know that this has 2 to the 1 elements, right? Because this kind of, in a way, is made well, it's made from a set that has only the 1 element. So I know that the power set is 2 to the 1, right? Or 2, right? The same thing is here, right? This is basically what we're going to do, right? Except that we're going to do it in general instead of just doing it with 1 element and then the power set has, 2. Here we're going to have that it has k elements, and so the power set must have 2 to the k elements in it too. Right? Because if we think about it, 1 is either in the subset or it's not in the subset. Right? So then if I want to think about we could count up what's the size of the power set, right? So the power set of, in this case, our set 1, 2. Well, notice that what I could do is I can just take this. Okay. And so let's go back in. Let's go back into this. Right. So let's choose some A in A prime. Right. And let's make, right? Let's make this argument. Right? I'm going to make a set S, right? 1. It's the set of all, let's say, subsets. In this case, hold on, let me. I'm going to make a set of all, we can call it whatever we want. I guess I could call it B. The set of all B in the power set of A prime, such that X is an element of B. Right? It's 2. Now just think back to what we were doing before with the first one, right? I was making these subsets, but with these specific numbers. In this case, I'm just making them general. So this is all B in prime. X is not an element. Right. So we've got these two. Now remember, when we did the sort of very small example, we talked about them being mutually exclusive sets, meaning that the intersection is actually the empty set. A very nice thing also about these two sets is that their union, right? Remember, the union of the two sets is actually the entire power set, right? So that's super handy for us. Now, what can we think about? Well, if I think about the way these are created, right, that we have this set, right? I'm going to call it A prime, right? And what I'm actually going to do is I'm going to take out A, right? What's the size of this? Well, this is actually a k-element set, right? And so what do I know about the power set of this, right? Well, I know the power set of everything that doesn't contain A is going to be 2 to the power k, right? So what do I know, right? I know that the, let's say the, let me go back. I guess not. Let me write that the power set, right, of this A prime, right, that's going to be 2 to the k, right? So we know that if it has, we have k plus 1 elements in A prime, but if I take one element away, I would know that there's 2 to the k, right? So what does that mean? It means that S1 or S2, I guess the power set of S2 is 2 to the k, right? And if this was 2 to the k, I also know that basically I just take all of the things that were in S2, right? I union them with A, right? And I get whatever S1 happens to be, right? So if we think about what happened here, my S2 from here, notice that if I take the empty set and I union it with the set 1, I'll just get the singleton set 1. And if I take the set 2, right, as over here, and I union it with 1, right, I'll get the set 1, 2 that's in S1. So notice that I can basically just see that since this is 2 to the k, I know that the size of the power set of S1, right, is also equal to 2 to the k. Right. Right. And how do I know this? Well, this was the thing I supposed, right? If I have a set that has k elements, right, now that the power set of that set actually has 2 to the k elements. And so we're almost done now. So now all I need to do is to show that if I want to find the power set, right, what do I know? I know that the power set of A prime, right, should actually just be the union the union of set S1 and S2. Right. So then and like before, right here, I've got that this is actually 2 to the k plus 2 to the k. That's 2 times 2 to the k, which is just equal to 2 to the k plus 1. That was quite a long proof, but I really wanted to go through the details so things make some sense. So